Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 5.6, day 2, entitled Modeling Harmonic Motion. And today we're going to talk more about damped harmonic motion. The previous section of notes talked about the simple harmonic motion. So damped just tweaks that a little bit. And it has a different equation. But basically what happens is when you have damped harmonic motion, it means that you have friction in your real world situation as well. So that friction is going to cause the motion of the object to slow down and eventually stop or get really, really small. So that means that the amplitude for these graphs isn't going to be the same and cyclical over and over and over again. It's going to actually decrease over time. So we're still going to have our sine and our cosine functions, and we're still going to have a constant for our amplitude. So that k value is going to be our amplitude. And then we're still going to have our period and our frequency. So we're still going to have 2 pi over w because we still have the w in our equation here. And we can still find frequency, which will be the w over 2 pi, like we saw in the previous section of notes. So those two concepts are the same. The other thing that's different in these equations is that we have E in there, but we've seen E and worked with E. We know what number he is. And then we're also going to have e to the power of negative c times t. And that's going to be true for both the sine and the cosine. And that c is going to be the damping constant right here. And they'll give you that information. And it's going to be negative because the graph is going to decrease over time. So that negative will make the graph decrease. Okay, so here's a good example, a couple pictures here of the simple harmonic motion that we talked about in the previous section of notes, where the graph is periodic, it keeps cycling over and over and over again. And then here's a picture of what the damped harmonic motion will look like. So that friction is affecting the graph and it's slowing down and decreasing our amplitude as we continue on over time. Okay, so we have two examples that we're going to take a look at. We're going to look at example 7 and 8. 7 is modeling damped harmonic motion, and here we have a two-mass spring system, or two mass spring systems are experiencing damped harmonic motion. Now both of them have a 0.5 cycle per second, so that's going to be the frequency. And both have an initial maximum displacement of 10 centimeters. So that's going to be our amplitude. So right here, this 0.5 cycles per second, that will be our frequency. Okay, so maybe let's jot that down here in between. Frequency, remember we find it by doing w over 2 pi. So that's going to be equal to 0.5. So that means we can solve that. We can actually multiply the 0.5 by the 2 pi, and we'll get our value for w, which will be 1 pi. And then the other piece of information here, this maximum displacement of 10 centimeters, that's going to be our k value. Oops, that's supposed to be a k. So that's like our amplitude. Having issues writing. That we were working with in the previous sections of notes. Okay. Now if we continue on, it tells us that the first damping constant is 0.5 and the second damping constant is 0.1. Okay, so those are those C values. So I think we have everything that we need for this equation because T in the equation will stay time. Okay, so we figured out, or they told us what K was. We figured out what W is. They told us what C is. So now we have T left over, but T will always stay time. Okay, so for part A, it says find functions in this form to model both cases. So again, we have our K, we have our W, and we have our C. So we can go ahead and write those equations. So let me write one of them up here. We'll have G of T equals 10 was our constant times e to the negative, let's just do 0.5 first, t, and then it'll be the cosine of 1 pi, or just pi, times t. So that's one equation. The other equation I'll write down here, g of t equals 10 times e to the negative 0.1 t cosine pi times t. So those would be our two equations. And then for part B, it says to graph these and then see how they differ. Now I would graph them one at a time, and I would graph them in your graphing calculator. Okay, this is going to be a pretty complicated graph, especially since we have this e to the negative 0.5 or e to the negative 0.1. Okay, that's going to be really hard to graph by hand. So we definitely want to do this on our graphing calculator. And you want to adjust the windows so that you can see what's going on. Remember, you can do zoom 7 for the trig option in your graphing calculator, or we know that our amplitude is 10, okay, and that we're starting at about, you know, 0.5 for our frequency. So, I mean, at least to do positive 10 to negative 10 in both directions on the x and y axis. You could also do, you know, bigger than that to make sure you can see it all. Go maybe up 20 and down 20 on the y-axis and out 20 and back 20 on the x-axis. Okay, this is what your book chose to do. Okay, they adjusted the window to go from -1 to 15 and then from 12 to -12. So since our amplitude was 10, they wanted to be able to see that. Okay. And then they went out 15. I don't know why they chose the value of 15. Maybe just looking at some of the values in the table of values after you plug in the equation. That's what they chose. We don't have to go way far back on the x-axis because that would be going back in time. Okay, so even if you started by doing that, you would see that, oh, you know, your graphing calculator is going to graph it over there, but we wouldn't need it in this case, okay, because it wouldn't make sense for our real world situation. Since that x-axis is our t value and that's time, going back here would be negative time. Okay. So this is a graph of our first function, this is a graph of our second function, and what you want to really conclude here is that the larger constant, this damping constant, slows the graph down faster. Okay, here we had a smaller constant, so the graph is still slowing down, but it's just taking a long time to slow down. So you'll have some problems in your homework as well where they want you to write the equation, graph it, and then make some conclusions about it. That's the conclusion. Okay, so example 8 then is dealing with our vibrating violin string. And it says here that a G string on a violin is pulled a distance of 0.5 centimeters above its resting position and then released. Okay, so you're pulling it up high and then you're letting it go. So this right here is telling you a couple pieces of information. It's telling you your amplitude. Okay, our K value is going to be 0.5. And it's also telling you whether or not you're going to do a sine or a cosine function. Okay, so the string is pulled all the way up. It's pulled a certain distance and then it's let go. So the starting position is higher up. Okay, so that's going to tell us that if I was to graph this, I'm not starting at 0 and then going up and then down. I'm starting up and then I'm coming down. So this is telling me that I'm doing a cosine function. So as you read these types of problems in your homework tonight, take a moment and think about that. Think about where is this particular object starting? Whether it's a string or it's a weight or it's a break or whatever. Okay, think about where it's actually starting to move. If it's sitting at a neutral position and then it gets moved up, that's going to be a sine. But if it's getting pulled up or pushed down and then released, that's going to be a cosine type of a situation. Okay, so let's continue on here. We have the damping constant is 1.4, so they told us that. Okay. And then suppose that the note produced is a pure G, which has a frequency of 200. So that means that they took W divided by 2 pi and they got 200 when they simplified that. So now we're going to have to multiply both sides by 2 pi so that we get W to equal 400 pi. So there's our value for W. So that's what that last piece of information told us. So now it says find an equation that describes the motion at the point at which the string was plucked. So we know we're going to use the cosine function. Okay. And let's just call it, f of t, a function of time. Okay. Our amplitude is 0.5. And then we have e, and then we have our constant. So negative 1.4. We need our t there as well. We said it's going to be a cosine function because we're starting up high. And then we have our frequency, 400 pi times t. So putting the equation together isn't necessarily hard. It's just being able to decipher the information from the problem. Being able to read them thoroughly and figure out, what distance is it? And that's my amplitude. Is it a sine or a cosine? What's my frequency? Okay. Luckily, they tell you here your frequency is this. So then you just take that little frequency equation and set it equal to 200, and that'll help you find your value for W. That's going to be very common to have to find that value for W first before you put it into your equation. So definitely practice these problems. There's not too many of them. The odds are in the back of the book, so you can check them. The evens are also worked out in the binder in the classroom. And if you have any questions with these application type problems, come on in and see me before school.